which is a very strange, confusing theory that I think people have often heard the name of, but don't know much about. But I want to kind of get across the fact that actually it's something we do experiments on. It's the kind of thing that actually has made its way into technology, and it's a real thing. It's not just a theory. And most importantly, I want to explore kind of the question of if quantum mechanics predicts all these strange things, and why isn't the world around us more strange? So of course I have to start in telling you a little bit of quantum mechanics, and the most obvious place to start is with a classic experiment called the two slits experiment. And what you do is you imagine that you have a sheet with two little holes in it, and you fire things at it. And so the first thing I'm going to fire is a wave. So a water wave, or a light wave, or a sound wave. Waves are quite intuitive, you understand what they mean. And so I've got a little diagram here. And what this shows, ironically, for a talk involving lasers, I don't have a laser pointer on this, but at the bottom, those straight lines meant to be waves going up towards this black sheet, which has a couple of, has a couple of holes in it. And you see the water waves, or the sound waves, kind of spreading out after this. And this makes some sense. You can imagine dropping a stone on a pond and seeing ripples going out. This isn't weird. And then we think of an important property of waves, which is that they add up. So if you have the top of two waves come together, they add up and get an even higher wave. And if you get the high bit of the wave and the low bit of the wave together, they cancel out and you don't get anything. And so this is what the bit of the wiggly line at the top is showing. I put some screens some distance away and I said, well, at each point, how much wave is there? And so you get bits where there's not very much wave at all, like here. You get bits where there's loads of wave, and interestingly, you get the most wave directly opposite the block between these two slits. And this is called interference. And it's not a strange thing with sound. In fact, you'd probably get it in this room if you listen carefully. There'll be spots all along the back wall where I won't be as loud as some other places where I'm really loud. So it's not strange. So now I go to the other extreme and I say, what if I fire a particle at it? So what do I mean by a particle? It could be a bullet, a tennis ball. Imagine if I have a big sheet and it's got two slits in it and I just drop tennis balls. What will I see on the other side? I'll see two piles of tennis balls opposite these slits. So people started doing experiments though, where they got very, very small particles. And I've actually gone for a big small particle here, which is popular molecule called Buckminster fullerene, which is 60 atoms of carbon. And so experiments were done where they fired these at the sheet with two little slits in it. And so what do you see? Well, it's a particle, right? You can see it with a maybe an atomic force microscope, but it's it's a particle, it's a ball, it's got a shape. You can do spectroscopy and they see its shape. And when they did this experiment, they saw a very strange thing, which is they saw interference on the other side. So they could fire one of these through at a time, and they say, well, where do they hit some screen at a distance? And they saw most of them hit, again, at the solid bit between the slits, and they saw this interference pattern. So it's strange. But then I asked myself, okay, well, I just don't understand particles. Particles are waves, and I'm confused somehow, I've been tricked. Particles are just waves. But it's more confusing than that. So what you can do is you can block one of these slits, and if I block one of them, so you just go through one of the slits, and I say, what do I see? And what I see is they all pile up on the other side of this slit, even if I do it one at a time. And the only explanation we can come to is that it goes through both of the slits at once. We justify that a little bit. If I send one particle, just one at a time, and it behaves as if it's gone through these slits and interfered like a wave, but it knows if I block one of those slits, it must have gone through both of the slits at once. And the way we think about this in quantum mechanics, we say it has gone through both, and it's in two places at once. It's been through both of those slits at once. It must go through both at once. This is the strange thing about quantum mechanics I'll focus on here. And it leads me to the immediate question of, can I be in two places at once, right? Because it's all very well, they've done this with electrons, with photons, with other molecules, but it's not the real world around us. I want to know, does this impact on me? Can I be in two places at once? So you have to think a little bit and go back to the quantum mechanics and say, there I am, about to fill my lungs with fibre insulation, actually. And I'm going to say, where am I? So quantum mechanics gives me an answer for where I am. It says I'm in lots of places at once. I'm spread out. The technical term is I'm in a superposition of places. And the amount I'm spread out be measured. And so this is a graph in the top left. And so it says, well, where am I and how likely am I to be there? So I'm really likely to be right on top of it. And I've got some kind of spread, which I call the size of my quantumness, or the size of my weirdness. So how big is this spread? So how weird am I? And it depends actually on quite a lot of things. So if I was to go for a little stroll at walking pace, then the amount I'm spread out by is this number here, 10 to the minus 27 meters. Now, you often hear, I do anyway, on the news, people trying to explain these massive amounts of debt that people are in, trillions and stuff, and that's like 10 to the 12 kind of numbers, and this is 10 to the minus 27, so a tiny number. What does this mean? What this means is, if I was the size of the Milky Way, if I was the size of a galaxy, I would know where I am, or the size of my quantumness, or my weirdness spread, I would think of it, is the size of a virus. Okay. So hit a dead end, right? I am not weird, and I never will be weird. My quantum nature is so small that you're just never going to see it. But I've glossed over some things. And part of the reason my quantum nature is so small compared to my size is that I'm big, I'm heavy, I've got a lot of energy, and I'm quite hot. That didn't sound so good in practice, actually. So I'm a room temperature at the very least, and the atoms in my body are jigging around. I'm hot, and that masks my quantum nature and makes it really tiny. And you can get over this by making things really cold. And that's why these quantum effects work for very small things like molecules, because they're so small, they've got so little energy already. It doesn't take so much to get their quantumness to be bigger than themselves, so they start to spread out. How do I make things really cold? And lasers are a really great way of making things cold. And I'm not going to talk much about lasers or the technical ways in which lasers make things cold, although I know it's a bit confusing. People think of lasers cutting through things. But we'll discuss a couple of properties of a laser, which I can explain. So I've got two pictures here. And on the left I have a torch, normal light, which is shining through some fog. And on the right I have some lasers. And so I asked myself, what's the difference between these two kinds of light? There's loads of differences between photons and platform. So one is the lasers have this lovely colour, and they have a very fixed colour. And that, for us physicists, that's equivalent to saying a very fixed energy or wavelength or frequency. All these things are very equivalent. So they've got very well-defined energy, and that means you can deliver a very well-defined amount of energy to something. And then the other really important property I'll pick up here is one that I think people often think is a technical point, which is you get these lovely thin beams of light. And this is not just a technical point, it's fundamental to the laser. It's actually very much related to the fact it's a single colour. And it means that you can deliver your energy, and these lasers are strong, to a very small place. So if I say I have a 10-watt laser, that's a really powerful laser, but a 10-watt light bulb isn't very powerful. That's because it's spewing out radiation all over the place and getting hot. But this is delivering a thin beam of focused energy to a place. And so the first way in which lasers are used to cool down things are with atoms. And this is a subject of my PhD in, so it's quite close to my heart. I'm not going to go into it in detail at all. And all I'm going to tell you is that light can push on things. There are ideas of having satellites with big sails, and the light from the sun pushes them along. It pushes, but very gently. Atoms are very, very light. And then actually the quantum mechanical nature of atoms also means that they see light in a slightly different way, in as much as you can get a resonance, like in a musical instrument, you can enhance this force. So the people who did this in the first place are Steve Chu on the left, who's the Farmers Energy Secretary in Bill Phillips and Bill Tanuji. And you can make, using lasers, you can cool atoms down. You make these amazing clouds of cold atoms. So this is just a webcam image from my PhD. So it's a few million atoms at a few thousandth of a degree above absolute zero, just sitting there levitating in laser beams. And these are amazing things, and you can cool them down so cold that their quantum nature becomes just as big as the cloud they're in. You have a quantum object and it interferes, and it's great. There's nothing like it in nature. In a strange way, there is this old physics. So I want to think about, can I go bigger? I'm going to have to speed up as well. So these atom clouds are a few million atoms. A full stop, which is the classic size of thing that seems to be 10 to the 18 atoms, so we're nowhere near the same kind of scales here. there's a really new field which is called optomechanics, which is what I study now, and that means the interaction of light with the motions. And it's laser cooling, but it's different kinds. And the traditional way of thinking about it is, imagine I have two mirrors, these are mirrors, and I get a bit of light in there. I get a light wave standing in there. And because it's two mirrors, the light bounces back and forth. And because it's a wave, it adds up and it adds up and it adds up. And I can get very, very, very strong light. So even though the force of light is very small, because there's so much light in there, I can start to exert a force on a big object. And so the light can exert a force on something. Here I've got a picture of a ball in this light wave. But also it disrupts the light. And so then where the ball is needs to depend on how much light there is in the cavity. Obviously two mirrors are cooled and vice versa. So as it moves through, it changes the intensity of the light in there. And this kind of really strong coupling between where this particle is and the strength of the light means you can transfer energy from this moving ball, say, to the light and take it away. And if you slow something down, it's getting cold. I don't have time to talk about temperature. That's a definition of temperature. It can get very cold. And at this point, this will be something you can see with your eye, and it'll be in two places at once. This is a picture from our experiment at UCL. And this green ball here is a little glass sphere that's being levitated by laser beams, held up by nothing but light in there. And so we hope to be able to cool this down. I haven't done it yet, to a point at which it's in two places at once, something you can see. Here's like an artist's impression of it in this cavity and picture. So in my last probably 2 minutes, which is just about enough time, I'm going to kind of speculate. Because although this is really exciting to me, if I can see something and I can then get that thing to behave in a quantum mechanical way and be in two places at once, how far can I take this? So I introduce my friend the tardigrade, or moss piglet, or water bear, depending where you come from. And these are tiny insects and they're incredible things. So they've been found on the top of the Himalayas. Being found all and at the bottom of the sea. They're basically everywhere, these things. And they're indestructible. So they've survived up to 155 degrees C. No one can cool one down, hold it up to its die. And it can survive 1,000 more times radiation than anything else that lives. Anything. And then my favourite thing someone's done with these is they took them up into space. They took some of these little insects up into space and just let them go. But probably into kind of insect pen of some kind. And then after 10 days, which is the length of the mission, we brought them back, right? And they're dead. They're all kind of like this, and they're dead. They woke up. They've been hibernating. They woke up and instantly started laying eggs, right? So these things can survive in space. And the reason I say this is because these kind of experiments we do have to take place in a vacuum, and the lasers might heat them up, and there's some radiation and such like. So this is actually something that's small enough you could potentially trap it in a light field. And if you could start to cool one of these down to the quantum level, what does this mean? I don't know if an insect can think as we understand thinking, but it's certainly getting close to that point. It can feel, it can sense, right? So what would you sense if you were in two places at once? So this is really starting to push the boundaries of what life means in a quantum mechanical sense. And this is the kind of technology which is hopefully like a few years away, not like 100 years away. The kind of time at which experimentalists can look at the quantum mechanics of life. And I think I'll leave you with that. Okay, thank you.